The histories you take, in the medication lists you review, in the dietary recalls you collect from patients who are genuinely trying to understand how they arrived where they are. The irony is this: the people most committed to eating well are frequently the people most systematically misled about what eating well actually means. They have read the labels, they have followed the guidelines, they have substituted the foods they were told were dangerous for the foods they were told were safe. And they are sitting in front of you with progressive insulin resistance, with blood sugar that will not stabilize, with a metabolic trajectory that the standard dietary advice they followed was supposed to prevent, and in some cases, quietly accelerated. Insulin resistance is the condition in which the cells of the body become progressively less responsive to insulin's signal to absorb glucose from the bloodstream. It is the foundational metabolic dysfunction underlying type 2 diabetes, a major driver of cardiovascular disease, and a contributor to conditions ranging from polycystic ovary syndrome to non-alcoholic fatty liver disease to certain forms of cognitive decline. It develops silently over years, and it is driven not only by the foods that everyone already understands to be problematic, the obvious sugars, the fast food, the heavily processed products whose poor nutritional profile is no longer seriously disputed, but by a set of foods that carry genuine reputations for health and that are consumed daily, in good faith by millions of people attempting to manage their metabolic health responsibly. These are 8 of those foods. The mechanism behind each one is specific and well documented. The clinical consequences of continued consumption in the context of existing or developing insulin resistance are real. And the fact that most people eating them have no idea they are contributing to the problem is not a personal failure. It is a failure of the information environment in which dietary choices are made. Fruit juice occupies a position in the public nutritional imagination that is almost entirely disconnected from its metabolic reality. It is fruit, it is natural, it is associated at the level of cultural assumption with health, with vitamins, with the kind of dietary choice that a health-conscious person makes. The glass of orange juice at breakfast is not a guilty pleasure. It is, for most people who consume it, an expression of genuine nutritional intention. The metabolic reality is considerably less benign. When fruit is juiced, the fiber matrix that surrounds and encapsulates the fruit's sugar content is disrupted or removed entirely. In whole fruit, that fiber slows the rate at which fructose and glucose are absorbed into the bloodstream, attenuating the glycemic response and providing satiety signals that regulate how much is consumed. In juice, those sugars are free, dissolved in liquid, absorbed rapidly through the intestinal wall, delivered to the liver and bloodstream in a concentrated surge that the body was not designed, evolutionarily, to manage in that form or at that speed. Fructose, the primary sugar in fruit, and therefore in fruit juice, is metabolized almost exclusively in the liver. Unlike glucose, it does not require insulin for its initial processing, which has led to the erroneous conclusion in some nutritional circles that it is therefore metabolically safer. In reality, the liver's capacity to process fructose is limited, and when that capacity is exceeded, which happens readily with liquid fructose delivery, the excess is converted to fat through a process called de novo lipogenesis, contributing directly to hepatic fat accumulation. Non-alcoholic fatty liver disease and hepatic insulin resistance are the downstream consequences, and hepatic insulin resistance is one of the primary drivers of systemic insulin resistance. Research published in the American Journal of Clinical Nutrition demonstrated that regular consumption of fructose-sweetened beverages increased hepatic fat, reduced insulin sensitivity, and elevated fasting insulin in overweight adults over a 10-week period. Fruit juice was among the beverages examined. The word natural on the label did not alter the metabolic outcome. Yogurt is in its plain, minimally processed form one of the more metabolically supportive foods available, a source of high-quality protein, beneficial fats, and live bacterial cultures that support gut microbiome diversity, which itself has an emerging and important relationship with insulin sensitivity. The yogurt that the majority of people consume, however, is not that product. It is flavored yogurt, the fruit on the bottom varieties, the low-fat strawberry and vanilla options, the yogurt drinks marketed to children and adults alike as healthy, natural, and nutritious. The transformation from plain yogurt to flavored yogurt involves two changes that are, from an insulin resistance standpoint, the wrong changes in both directions simultaneously. Fat is reduced or removed, which, as with the broader low-fat dietary paradigm, eliminates one of the primary factors that slows gastric emptying and buffers glycemic response. And sugar is added, often in quantities that place a single serving of flavored yogurt in the same category as a confectionery product, despite its positioning in the health foods aisle. A standard 150-gram serving of a popular low-fat fruit yogurt commonly contains between 15 and 20 grams of added sugar. Consumed at breakfast in the window of morning insulin resistance, alongside other carbohydrate-containing foods, this represents a meaningful addition to the glycemic load of a meal that is already, for most people, the most metabolically demanding of the day. The low-fat labeling compounds the problem further by creating a halo effect, the perception that because one nutritional metric has been improved, the product overall is virtuous. It is a perception that the food industry has understood and exploited with considerable commercial success, and it is one that the metabolic research literature has spent decades quietly contradicting. Full-fat plain yogurt with no added sugar, to which whole fruit may be added in controlled quantity, is a fundamentally different metabolic proposition from the flavored low-fat alternative that occupies most of the yogurt shelf. The breakfast cereal category deserves direct and detailed examination, both because of how extensively it has been marketed as a health food and because of how comprehensively the metabolic evidence contradicts that positioning. The glycemic indices of many mainstream breakfast cereals, including products marketed specifically on platforms of heart health, fiber content, and whole grain composition, rival or exceed those of recognized high-sugar foods. Cornflakes, rice-based cereals, and many branded bran and whole grain products produce postprandial glucose responses that place them in the highest glycemic tier of commonly consumed foods. The processing involved in cereal manufacture is the primary explanation. Even when whole grains are used as the starting material, the extrusion, puffing, flaking, and high-temperature processing involved in converting them into shelf-stable breakfast products disrupts the physical structure that gives whole grain its glycemic buffering properties. The intact grain architecture, the outer bran layers, the aileron, the germ, slows digestion and moderates glucose absorption. The extruded puffed or flaked equivalent has had that architecture mechanically destroyed, leaving a carbohydrate that the digestive enzymes can access rapidly and completely, producing a glucose delivery profile far more similar to refined white flour than to the intact whole grain from which it nominally derives. Research published in the European Journal of Clinical Nutrition demonstrated that processing method was a more significant determinant of glycemic response in grain-based foods than grain type itself, meaning that a highly processed whole grain product could produce a greater blood sugar spike than a less processed refined grain product. This finding directly undermines the nutritional logic of choosing breakfast cereals on the basis of whole grain labeling alone, and it has significant implications for the millions of people who have made that substitution in good faith as part of an effort to manage their blood sugar or reduce their diabetes risk. Agave syrup arrived in the health food market as an apparently rational alternative to refined sugar, lower on the glycemic index, natural in origin, derived from a plant with genuine traditional uses. It was adopted rapidly by the health-conscious consumer segment and embedded itself in the ingredient lists of products positioned across the organic, natural, and health food categories. The nutritional reasoning behind its adoption was not entirely without basis. Agave does have a lower glycemic index than table sugar, and it does produce a smaller acute blood glucose spike in isolation. The problem is that the glycemic index captures only one dimension of a food's metabolic impact, and in Agave's case, it captures the least relevant one. Agave syrup is among the highest fructose sweeteners commercially available, with fructose content ranging from 70 to 90% depending on the product, compared to approximately 50% in table sugar and high fructose corn syrup. The lower glycemic index is a direct consequence of this high fructose content. Fructose does not raise blood glucose acutely because it is not processed through the insulin glucose pathway in peripheral tissues. It is processed in the liver and as described in the context of fruit juice, repeated high-dose fructose delivery to the liver promotes de novo lipogenesis, hepatic fat accumulation, and hepatic insulin resistance with a consistency and mechanistic clarity that the research literature has established firmly. A study published in the Journal of Clinical Investigation directly compared the metabolic effects of glucose and fructose consumption over 10 weeks in overweight adults and found that fructose selectively increased visceral adiposity, hepatic fat, fasting insulin, and markers of insulin resistance, effects that were not observed with glucose consumption at equivalent caloric levels. Agave syrup, precisely because of its exceptionally high fructose concentration, represents a more potent driver of these outcomes than the sugar it was adopted to replace. Its reputation as a health food is, in metabolic terms, an inversion of its actual biological effects. Bread is among the most culturally embedded foods in human dietary history, and the nutritional guidance of the past several decades has been relatively consistent in positioning multigrain, wholemeal, and brown varieties as meaningfully superior to white bread for metabolic health. The guidance is not without foundation. Genuinely whole grain bread made from minimally processed grain with intact bran and germ does have a lower glycemic response than highly refined white bread, and the fiber content of authentic whole grain products provides genuine benefits for gut health, satiety, and postprandial glucose regulation. The commercial reality of the multigrain and brown bread category, however, is considerably more complicated than that guidance implies. A significant proportion of products labeled multigrain, seeded, or brown are made from refined white flour as the primary ingredient, with small quantities of whole grains, seeds, or coloring agents added to justify the positioning and the premium pricing. The ingredient list of many commercially popular brown and multigrain loaves reveals refined wheat flour as the first and therefore most abundant component, with the whole grain or seed content present in quantities insufficient to materially alter the glycemic response of the product. The bread looks and sounds different from white bread. Metabolically, it frequently is not. Even genuinely wholemeal bread made from flour in which the entire grain is retained produces a glycemic response that is, for many people, substantially higher than would be expected from its reputation. The milling of whole grain into fine flour, even without removing the bran and germ, dramatically increases the surface area available to digestive enzymes, accelerating glucose release relative to intact whole grain. Research comparing the glycemic responses of whole grain bread with intact whole grain kernels, sourdough preparations, grain berries, minimally processed grain products has consistently found that the form of the grain matters as much as its completeness. Intact, less processed grain structures, including genuine sourdough fermented for extended periods, produce lower glycemic responses than the same grain milled and baked by standard methods. The bread aisle, in other words, requires considerably more discrimination than the front-of-pack labeling invites. The sports drink category was designed for a specific and legitimate purpose: the rapid replacement of fluids, electrolytes, and carbohydrates in athletes engaged in sustained, high-intensity exercise lasting 60 minutes or more. In that context, the glucose and fructose content of a sports drink serves a genuine metabolic function. It maintains blood glucose during prolonged exercise, spares muscle glycogen, and accelerates recovery. The problem arises when the same products are consumed by people who are not engaged in that context, which in practice is the majority of sports drink consumers. A standard sports drink contains between 20 and 30 grams of rapidly absorbed carbohydrate per serving, delivered in liquid form with no fiber, minimal protein, and no fat, a macronutrient profile specifically engineered to maximize the speed of glucose entry into the bloodstream. For a resting or moderately active individual, this represents a substantial glycemic load with no exercise-driven glucose disposal mechanism to absorb it. The muscles, which in an exercising athlete are actively consuming glucose through the insulin-independent contraction pathway, are largely dormant in the person drinking a sports drink at a desk or during a gentle walk. The glucose has nowhere efficient to go. Insulin is released in response to the spike, and the metabolic consequences are the same as consuming any other high-sugar beverage without the physiological justification. Coconut water has acquired a health food reputation that places it in a different category in the public imagination, but its metabolic profile deserves examination on its own terms. Natural coconut water contains between 9 and 15 grams of sugar per 250 milliliter serving, primarily as glucose and fructose, with a relatively low fiber content and a glycemic impact that, while modest in isolation, becomes significant when consumed regularly, in larger volumes, and in the context of an otherwise carbohydrate-heavy dietary pattern. Its electrolyte content is genuine and has clinical utility in specific contexts of dehydration. As a daily hydration habit for individuals managing insulin resistance, however, it is a source of liquid sugar whose health associations are not matched by its metabolic reality. The low-fat dressing category is perhaps the most direct surviving artifact of the low-fat dietary era, a product category that exists entirely as a consequence of nutritional guidance that has since been substantially revised, and that continues to occupy a prominent position in the health-conscious consumer's refrigerator on the basis of a logic that the research community largely abandoned a decade ago. Fat in salad dressing serves two purposes that are both relevant to insulin resistance. The first is direct. Dietary fat slows gastric emptying and reduces the glycemic response of the meal with which it is consumed. Research published in Diabetes Care demonstrated that the fat content of a meal is an independent determinant of postprandial glucose response, with higher fat meals producing lower and slower glucose rises than lower fat equivalents of comparable carbohydrate content. Removing fat from a dressing consumed with a salad that may already contain carbohydrate from vegetables, legumes, croutons, or accompanying grains removes a buffer that was moderating the glycemic impact of the overall meal. The second purpose is indirect but equally important. Fat enables the absorption of fat-soluble vitamins and carotenoids, including vitamins A, D, E, and K, and compounds such as lycopene and lutein from the vegetables in the salad. Research published in the American Journal of Clinical Nutrition found that fat-free dressings produce negligible absorption of several key carotenoids from salad vegetables, while full-fat dressings produced robust absorption of the same compounds. The salad becomes, in nutritional terms, considerably less valuable than it appears. In place of the fat, low-fat dressings substitute sugar, modified starch, and a range of thickening and flavoring agents that increase the glycemic load of what was intended as a health-supporting meal choice. The substitution reduces the metabolic benefit while adding a glycemic burden, a combination that, for someone managing insulin resistance, moves in precisely the wrong direction. Dried fruit completes this list as perhaps the most nutritionally misunderstood food in the health foods category, present in trail mixes, granola bars, breakfast cereals, and health-conscious snack products, consumed as a natural sugar alternative and regarded broadly as a whole food option that carries the nutritional credentials of the fresh fruit from which it derives. The dehydration process that converts fresh fruit to dried fruit removes water, which is the primary component responsible for the volume and satiety effect of fresh fruit, while concentrating the sugar content per unit of weight by a factor of 4 to 8, depending on the fruit. A tablespoon of raisins contains roughly the same sugar content as a small bunch of fresh grapes that would occupy considerably more space in the stomach, generate substantially more satiety signaling, and be consumed more slowly. The fiber remains largely intact in dried fruit, which provides some glycemic buffering, but the concentration of sugar per gram, combined with the small serving sizes in which dried fruit is typically consumed, means that even modest portions deliver a glycemic load that exceeds what most people consuming them would estimate. Medjool dates, frequently promoted in health food circles as a natural sweetener and energy food, contain approximately 18 grams of sugar per date, a glycemic load comparable to a small confectionery item despite their whole food credentials. Dried mango, dried apricots, and dried cranberries, particularly when the latter have added sugar to compensate for their natural tartness, as is standard in most commercial preparations, all deliver concentrated fructose and glucose loads that are metabolically significant in the context of insulin resistance. A study published in Nutrition Research found that substituting dried fruit for fresh fruit in the diet produced measurably higher postprandial glucose responses and greater insulin excursion, finding that is consistent with the concentration mechanism described above, and that directly challenges the equivalence that most consumers assume between the fresh and dried versions of the same fruit. The 8 foods described here are not marginal contributions to the insulin resistance problem. They are, collectively, a substantial part of the dietary landscape that millions of health-conscious people navigate daily under the impression that they are making choices that support their metabolic health. The orange juice at breakfast, the flavored yogurt chosen over the donut, the multi-grain bread selected instead of white, the Agave sweetened granola bar from the health food shop. These choices are made in good faith, informed by a nutritional communication environment that has been shaped by commercial interests, oversimplified guidelines, and the persistent survival of ideas that the metabolic research has progressively dismantled. Insulin resistance does not develop because people are careless or uninformed about health in general. It develops, in many cases, because the specific information required to make genuinely metabolically supportive choices has not been communicated clearly, specifically, or honestly enough. The gap between the public reputation of these foods and their metabolic reality is not a gap that exists at the frontier of nutritional science. It is a gap that exists in the translation of established science into the information that reaches people at the moment they are making dietary decisions. Understanding the mechanisms, why fructose in liquid form behaves differently from fructose in whole fruit, why processing method matters as much as grain type, why fat removal from a dressing changes the metabolic character of an entire meal is not academic knowledge. It is practical, applicable, and immediately relevant to the daily choices that determine, over years, whether insulin sensitivity is maintained or progressively lost. The emergency medicine perspective on this is straightforward. The patients managing the consequences of advanced metabolic disease did not, in most cases, eat carelessly. They ate according to the best information they had. Giving people better information earlier, more specifically, and with a clearer account of the underlying biology is not a secondary clinical priority. It is one of the most direct interventions available.